today we're going to make sure we can use the chain rule with trigonometric functions. Of course, we started off by learning the power rule, where to get the derivative of x to the third, you simply move the power 3 into the front and then subtract 1 from that exponent. We then moved on and learned the chain rule, which is very similar to the power rule. To get the derivative of this function, I'm still going to move the power of 3 into the front, and then I'm going to subtract 1 from the exponent. The only additional step is we need to multiply by the derivative of 2x squared. And of course, the derivative of 2x squared is 4x. I suppose I can neaten this up a bit. The 3 times 4x is 12x, and the 2x squared to the power of 2, well, 2x squared to the power of 2 is 4x to the power of 4. 12 times 4 is 48, and x times x to the 4 is x to the power of 5. The chain rule is very similar to the power rule in the fact that you move the exponent into the front and then subtract 1. It just has that one additional step where you need to multiply by the derivative of this piece. Well, we're hopefully going to see that the same logic applies with our trigonometric functions. The derivative of sine x is cosine x, and that means the derivative of sine 2x squared is cosine 2x squared. But there is going to be one additional step. We're now going to need to multiply this by the derivative of 2x squared, and the derivative of 2x squared is 4x. Now, to multiply cosine of 2x squared times 4x, we're certainly not going to multiply the 2x squared times the 4x. What I'm going to do instead is move this 4x into the front. I'm going to say the derivative is 4x times cosine of 2x squared. Let's take a look at some more trigonometric functions that we can differentiate using the chain rule. Of course, to have success with differentiating these functions, you really need to know your 6 trigonometric derivatives. I know the derivative of sine is cosine, so the derivative of sine 2x is cosine 2x. But then I need to multiply by the derivative of 2x. I need to multiply this by 2. And of course, cosine of 2x times 2 is not cosine of 4x. It's 2 cosine 2x. Perhaps that's a bit more obvious if I think of cosine 2x like this. I know the derivative of cosine is negative sine, so the derivative of cosine of x plus 1 is negative sine of x plus 1. But then I need to multiply by the derivative of x plus 1, and if you think about it, the derivative of x plus 1 is just 1. So f prime of x is negative sine of x plus 1. Here I'm asked to get the derivative of tangent 3x. I know the derivative of tangent is secant squared, so the derivative of tangent 3x is secant squared of 3x. But then I need to multiply by the derivative of 3x. The derivative of 3x is, of course, 3. Once again, we're certainly not going to multiply this 3x times 3. It's 3 times secant squared 3x. To have success with number 4, I think it would be a good idea to rewrite this in a way more indicative of what it actually means. Of course, cosine squared x means cosine x times cosine x, or cosine x squared. And when it's written this way, perhaps you see it resembles a function we can get the derivative of using the power rule. It's something squared. So to get the derivative, I can move the 2 in the front and then subtract 1 from the exponent. So I guess that would be 2 cosine x to the power of 1. But then I must multiply this by the derivative of the inside here, and the derivative of cosine of x is negative sine x. And then I can say positive 2 cosine x times negative 1 sine x is negative 2 cosine x sine x. Let's be careful on this last one. I know the derivative of secant x is secant x tangent x. So the derivative of secant 5x is secant 5x tangent 5x. But I can't forget I need to multiply by the derivative of 5x, and the derivative of 5x is 5. I don't need to multiply both of these by 5. I just need to multiply secant 5x tangent 5x times 5. So my y prime is 5 secant 5x tangent 5x. Here I have 3 functions that, when read aloud, all sound the same. Cosine 3x squared, cosine 3x squared, cosine 3x squared. But of course, I'm sure you know, these are 3 different functions, and they'll have 3 different derivatives. Let's first get the derivative of f of x. I know the derivative of cosine is negative sine, so the derivative of cosine 3x squared is negative sine 3x squared, but then I have to multiply by the derivative of this piece, and the derivative of 3x squared is 6x. This is of course more appropriate to write with the 6x in the front. I'm going to say f prime of x is negative 6x sine of 3x squared. In this first example, the exponent of 2 had a base of x. Well, in this example, the exponent of 2 has a base of 3x. Of course, 3x times 3x is 9x squared. I could rewrite this as cosine of 9x squared. Let's get the derivative of cosine 9x squared. The derivative of cosine is negative sine, so the derivative of cosine 9x squared is negative sine 9x squared. But then times the derivative of 9x squared, so times 18x. Let me move my 18x in front of sine. This last function may look sort of strange to you because it is sort of strange. This is not a common looking function. This cosine of 3, let me point out to you, cosine of 3 is simply a number. It's not a number you should know off the top of your head. You should know what cosine of pi over 6 is, or cosine of 5 pi over 4 is. Cosine of 3 is a number you would need a calculator to find. But it is just a number, which means you would approach this just like you would getting the derivative of something more common, like 5x squared. To get the derivative of 5x squared, when you move the 2 in the front, you multiply 2 times 5. So to get the derivative here, when I move the 2 in the front, I'll multiply 2 times cosine 3. So my new coefficient is 2 cosine 3, and then that's times x to the power of 1. I don't need to apply the chain rule here because cosine of 3 was a constant multiplier. I simply had a coefficient, a variable, and an exponent. I just used the power rule. All right, don't worry too much about that last example. We're not going to encounter functions like that very often. Getting the derivative of sine x is easy. To get the derivative of sine 4x, we need to apply the chain rule. My derivative is cosine 4x, but then I need to multiply by the derivative of 4x, or I need to multiply by 4. And we express that 4 cosine 4x. To get the derivative of a function like this, though, we should first rewrite it in a way more indicative of what it means. This means sine of 4x to the power of 3. I now have it written in a way where I can use what is sometimes referred to as the general power rule. I'm going to move the 3 in the front, move the power in the front, and then subtract 1 from the power, but then we just need to multiply by the derivative of sine of 4x. And we just saw a moment ago that the derivative of sine of 4x is 4 cosine 4x. Now let me see if I can neaten this up a bit. I have a coefficient of 3 and a coefficient of 4, so that would be 12. My sine of 4x to the power of 2, I could write as sine squared 4x, and then times cosine 4x. And finding derivatives like this is where this lesson gets a little bit tricky, so we better look at a few more examples. Here, finding the derivative of h of x can be a bit tricky, so I'm trying to take the approach of easing into it with some easier derivatives first. Of course, the derivative of cosine is negative sine, so the derivative of cosine x is negative sine x. Well, that means the derivative of cosine 3x squared plus 5 is negative sine 3x squared plus 5. But we, of course, have to multiply that by the derivative of 3x squared plus 5. We need to multiply that by 6x. And this, of course, would be more properly written with the 6x in front of the sign. Well, maybe now we're ready to approach getting the derivative of h of x, and the first thing I'm going to do is rewrite it in a way more indicative of what it means. This means cosine of 3x squared plus 5 all to the power of 2. And it's now written in a way where I hope you can see we can use our general power rule. We have a power of 2. To get the derivative, I'm going to move the power of 2 in the front. And then I'm going to take all of this and lower the power to 1. But finally, I need to multiply this by the derivative of cosine 3x squared plus 5. I need to multiply it by the derivative of what was in those brackets. And we saw just a moment ago that the derivative of cosine 3x squared plus 5 is negative 6x sine 3x squared plus 5. So to get this piece over here, you almost have to have tunnel vision and just consider the derivative of what's inside those brackets. Let's see if we can't neaten this up a bit. We have a positive 2 and a negative 6x, so negative 12x. Then we have a cosine 3x squared plus 5 to the 1, so that's just cosine 3x squared plus 5. And finally times sine of 3x squared plus 5. Not sure if you're catching it, but to get the derivative of a function like h of x, we're actually using the chain rule twice. To get the derivative of this function, I have a feeling I'm going to need to use the chain rule twice. Let's start by easing our way into it. I'm going to get the derivative of 2 times tangent x. I don't need to use the product rule because 2 is a constant multiplier. 2 is just going to come along for the ride. And of course, the derivative of tangent is secant squared. Same thing in this second example. My 2 is a constant multiplier. So 2 could just come along for the ride. And then the derivative of tangent is secant squared. So the derivative of tangent 3x is secant squared 3x. But we then need to multiply by the derivative of 3x. We then need to multiply this by 3. I can, of course, neaten this up. I can move my 3 in the front and multiply it times the 2. This would be 6 secant squared 3x. I'm sure you can anticipate that we're going to want to rewrite this one, but I hope you notice that the base of this exponent of 4 is tangent 3x, not 2 tangent 3x. This 2 is a constant multiplier, so when I rewrite it, this is 2 times tangent of 3x to the power of 4. It's now written in a way where we can use our general power rule. To get the derivative, I'll move my exponent of 4 into the front, so 4 times 2 is of course 8. I'll subtract 1 from the power of 4 to make it 3, and then I want to multiply by the derivative of the inside. I want to multiply by the derivative of tangent of 3x. Please note, this is not the derivative of tangent of 3x. This is the derivative of 2 tangent 3x. We only want to multiply by the derivative of this piece. The derivative of tangent 3x is secant squared 3x times the derivative of 3x, or times 3. Let's see if we can neaten this up. 8 times 3 is 24. I'm going to write this tangent of 3x to the power of 3 as tangent cubed 3x. And then, of course, I have my secant squared 3x. Is your head spinning yet?
Here we're being asked to find the equation of the line tangent to the graph of f at the point pi comma 1. When we're asked to find the equation of a line, we of course need a point and a slope. We have a point, we just need a slope, so we of course need to get the derivative. I'll first get the derivative of 2 sine x. I have a constant multiplier of 2, and the derivative of sine is cosine. Then I'm going to add the derivative of cosine 2x, which of course will require using the chain rule. The derivative of cosine is negative sine, so the derivative of cosine 2x is negative sine 2x times the derivative of 2x, or times 2. Let me neaten this up just a bit. Now that I know my derivative, I just need to find the slope of this graph at the x value of pi. Let's evaluate f prime of pi. Let me plug pi in for x. Let's evaluate cosine of pi. Here's pi, and cosine is the x value. Cosine of pi is negative 1. Let's evaluate sine of 2 pi. So 2 pi, of course, is right here, and sine is the y value. Sine of 2 pi is 0. So I have 2 times negative 1, or negative 2 minus 0. I now know my slope is negative 2, and I can write the equation of my line. So y minus the y value equals the slope times x minus the x value. Let's see what this looks like in y equals mx plus b form. I distributed my negative 2, and now let me add 1 to each side. It looks like my slope is negative 2, and my y-intercept is 2 pi plus 1. Let's see what the graph of 2 sine x plus cosine 2x looks like. And let's draw a line tangent at the x value of pi. Looks like my slope is negative 1.9999999, or negative 2, and my y-intercept is 7.28, which is of course 2 pi plus 1. All right, hope you had fun learning the chain rule.